Hello everybody, my name is Ethan. Welcome back to the channel where today we're hopping back into the machine learning course on Codecademy. In today's video, we are going to be doing hyperparameters in machine learning models. So in the previous episode or video, we did an introduction to regularization, and hyperparameters were a big part of it within L1 and L2 regularization. So if you missed that, kind of a bit of an introduction there. So we'll kind of go a little bit further in depth into hyperparameters and kind of explain what they are. So introduction hyperparameters are an important part of machine learning. We're going to explain what they do along with the examples of what they look like for different commonly used machine learning models. You'll learn why they're important and how they affect model performance, and you'll also learn about a few hyperparameter tuning methods that you can implement in your own projects. Okay, what are hyperparameters? A hyperparameter of a machine learning model is a value that determines part of the learning process and is not affected by training, unlike a parameter, which is learned during the model training process. You're probably already familiar with some hyperparameters. Let's look at some examples. In the k nearest neighbors algorithm, k is a hyperparameter. K determines how many neighbors will be used, and training data does not change k. Decision trees also use hyperparameters. Before training a decision tree classifier, you may want to specify how deep the tree can go, i.e. how many splits are allowed before arriving at a leaf. You may also want to specify the minimum number of samples that are present in a node in order to split that node. Both of these values are hyperparameters. They determine the structure of the model, but they are not learned during training. Regularization factors are another example. In linear or logistic regression, regularization is a term that is added to the loss function in order to penalize models with large coefficients. The coefficients are the parameters of the model here. The coefficients are the parameters of the model here. The regularization factor is a hyperparameter. The value of regularization factor affects how large the coefficients of a regression model will be. But I was very confused because they opened a parentheses here, but then never closed it. Never closed the parenthesis. The value of the regularization factor affects how large the coefficients of a regression model will be, but the regularization factor is independent of the training data. Hyperparameter tuning. Hyperparameters can make or break a machine learning model. Take the k nearest neighbors algorithm as an example. Recall that in k minus nn classification, or k nearest neighbors classification, the class of a sample is determined by the class of its k nearest neighbors from the training data. If k is too large, classes with a small number of samples might be missed, and the model could underfit the data. But if k is too small, it's possible that outliers in the training data could misclassify their neighbors. This model could be overfit to those outliers. This balance between overfitting and underfitting is called the bias variance trade-off. It's an important consideration for supervised machine learning, something that we did cover in the previous video. Bias. Bias is the difference between a model's predictions and the correct values. Models with a lot of bias underfit the data and will perform poorly on both testing and training data. In biased models, the structure of the model overpowers the training data. Variance. Variance refers to the dependence of a model on training data. A model has high variance if different training data results in widely varying outcomes. This often leads to overfitting a model to training data. Overfit high variance models generally perform well on training data, but perform very poorly on testing data. In this case, the training data overpowers the structures of the model. The bias variance trade-off is called a trade-off because decreasing the bias usually increases variance. The converse is also true. Decreasing variance usually increases bias. Good machine learning models strike a balance. We can reduce bias by making a model more sensitive to training data, but we do so at the risk of overfitting. On the other hand, we can reduce variance by restricting a model so that it is less affected by training data. This, however, runs the risk of underfitting the model. Ultimately, we want models that perform well on testing data. One way to do that is to choose the right parameters, or hyperparameters, In this case of supervised machine learning, we want hyperparameters that make good compromise between bias and variance. This can be done by training a model multiple times, each time with different hyperparameter values, and then using the best ones. This process is called hyperparameter tuning. There are several different ways of doing this. All right, so here are some common hyperparameter tuning methods. The grid search algorithm for hyperparameter tuning works by training a model on predetermined list of hyperparameter values. This method tries every hyperparameter value on list and then uses the one that makes the model perform the best. The random search algorithm works similarly, but instead of using a predetermined list of hyperparameter values, the values are randomly chosen. As with a grid search, it selects hyperparameters that performed best. Bayesian optimization is another approach to hyperparameter tuning. It uses ideas from the fields of Bayesian statistics to iterate through different hyperparameter values. Each time the Bayesian optimization algorithm evaluates a new hyperparameter value, it gains more information about where it should look for the best hyperparameter value. Genetic algorithms are another possible hyperparameter tuning method. These work by going through several generations of hyperparameter values. Within each generation, the fittest, i.e., best performing hyperparameter values are slightly mutated, i.e. changed, in order to produce the next generation. Each of these hyperparameter tuning methods will be covered in more detail in a subsequent lesson. You also learn how to implement each of them in Python. When tuning hyperparameters, it's important to split the data into training, testing, and validation data. Training data is used to train the model. Validation data is used to evaluate hyperparameters. After a hyperparameter is tuned, the model can be tested on testing data. This allows for an estimate of model performance that isn't affected by the hyperparameter tuning process. Here's an example. Say there was a classification problem. We want to tune a hyperparameter alpha. Say we want to determine whether the model performs best with alpha equals 1, alpha equals 2, or alpha equals 3. We'll train the model 3 times, once with each possible value of alpha. Since we're looking at a predetermined list of hyperparameter values, this is a grid search. Let's say the accuracy was as follows. So it looks like the accuracy on the training set was 85, 85, 88, but then on validation set, it was 80, 84, and 83. And then on the testing set, it's 82 for alpha equals 2. Since the model was most accurate on the validation set with alpha equals 2, we will use that value. However, we can't estimate the model's accuracy based on the data that was used to determine the model's hyperparameter. This would likely overestimate the actual accuracy. Therefore, we must measure the accuracy of the final model with alpha equal 2 on the testing set. Here, a table of that lists several machine learning algorithms, some of their hyperparameters, and possible tuning methods. This table is not exhaustive. Some machine learning models or machine learning algorithms have hyperparameters that aren't listed here. If you want to learn more, there's obviously in scikit-learn the documentation. It's going to be really hard for you guys to read this. I don't think I can read it. I don't know why they would think light blue on white would be a good idea, but whatever. Let's continue on. Okay, so here's the actual table now. Looks a little bit better when it's blown up like this. In this lesson, you learn about the different methods that you can use to tune hyperparameters in machine learning. Okay. All right, an introduction to the grid search method. We'll start with the grid search algorithm. Grid search works by testing a model. Sorry, I'm glowing right now. Grid search works by testing a model on a list of hyperparameter values decided on beforehand. Suppose we had 2 hyperparameters that we wanted to tune and we wanted to choose between 6 values for the first one and 5 values for the second one. We'd be searching a grid of 30 values as shown below. Grid search would fit the model and evaluate its performance for each of the values presented by these points. We then can choose the hyperparameter values corresponding to the best performance and conclude our hyperparameter search. In our case, where we're using a logistic regression model with regularization, we might want to make decisions on the following hyperparameter tuning. The type of regularization to use, the penalty parameter in scikit-learn represents this, and let's say we'd like to figure it out if lasso or ridge regression is the better choice here. The strength of regularization to use, scikit-learn's parameter C represents the inverse of regularization strength, and let's say we like to test 3 possible values, 1, 10, and 100. This means if we had to search a grid of 2 by 3, 6 values, grid search CV and scikit-learn lets us do this, test the model at each of these values to come up with the best possible set. from the list given. The two most important parameters in grid search CV is they need to be specified are the name of the model that we are testing and the name of a dictionary of hyperparameters that we'd like to initialize, represented by the argument parameters. To tune the hyperparameters, we can use .fit just as we would for regular machine learning model. We're going to be working with scikit-learn's breast cancer dataset. I've used Jupyter Notebook before, so I should be okay with this. All we'll have to do is click save and then run. You can run a notebook, so it's just okay. After running the setup cell, so we'll click run. We've run the setup cell. Create a logistic regression model called LR, since we want to use a solver that is compatible with both L1 and L2 regularization. Set the parameter solver equal to liblinear. The default solver does not support L1. Ensure that the model converges set max iter to equal to 1000. Okay. So we want to do LR is equal to logistic regression. I always add the extra I when I really don't need to. And it wants us to add two parameters here. Solver is equal to liblinear. And then also max iter is equal to 1000. And we'll save it now and run that. We can check our output by printing get parameters, I suppose. So let's do that. And we do. So very nice. Test work. Define a I am going to recomment this out just so we don't run everything out there. Okay. Define a dictionary parameters that you will be performing the grid on. The dictionary should have two keys. Okay, so parameters is equal to a dictionary. Should have two keys. Penalty and C. The regularization to be set. Oh, I see. So this one's a list 1, 10, 100. And for penalty, we want the two regularization types. And so L1, and it's saying to specify that it's lowercase because no reason, just make sure to specify lowercase. Okay. We'll save and then run it. And we'll click test work so we can continue on. We can now set up a grid search. Define a grid search CV object named CLF. The first argument is estimator, which corresponds to the logistic regression model you've created. And the second argument is param grid, which corresponds to the dictionary. Okay. So we can do CLF is equal to grid search CV. Our first argument is estimator. We're setting that equal to our linear regression model. And then our second one is param grid, and we're going to set that equal to parameters. We can now save this and run it. And we can test our work. We did it correctly. So this was exactly what we wanted. Nice. Okay. Evaluating the results of grid search CV. The CV in grid search CV is an acronym for cross-validation. Its best practice in machine learning is to go beyond the usual train test split and have a holdout or validation data set. Specifically, grid search CV uses a technique known as k-fold cross-validation. This works as follows. Cross-validation in grid search CV. Grid search CV subdivides the training data further into another training and test data set. It fits the model on this new training data set and evaluates the model on the new test data. But to make sure that we don't accidentally have good performance in only one part of our dataset, Grid Search CV will do this process multiple times on different cross-validation splits so that every point in the data gets to be tested at least once. The number of times this happens in the K is the K in K-fold. For instance, in a 10-fold cross-data validation, our data would be split into 90, 10, train test data split time 10 times, and Grid Search CV will evaluate the model on each fold. Okay. In scikit-learn, CV argument in Grid Search allows us to decide the number of cross-validation. The default setting for this is 5. After fitting Grid Search CV model, we can find out the results by the attributes of the CLF argument. Best estimator gives us the best estimator. Best score gives us the best. Gives us the mean cross-validated score corresponding to the best estimator. And best params gives us the set of hyperparameters that corresponded to the best estimator. Additionally, the .cv results attributes give us the score for each hyperparameter combination in the grid. We're now ready to evaluate the grid search we set up earlier and preloaded the code from the previous exercise in the cell up above. I'll press save, do the setup. Fit the grid search classifier to the drain data set. So we can do CLF is equal to grid search CV. Set the best estimator to a variable best model. I see. With the parameter, there's two parameters that we need. So first we have the estimator, and we're setting that equal to the linear regression, and then what it was called, parameters. Oh wait, I've already done this. Oh, fit the data. Did it tell us how to do this? I'm confused. How do we fit the parameter? Okay. It didn't tell us how to fit the data. CLF.fit to X train and Y train. Okay. We'll just do it that way. So then we'll do best model is equal to CLF dot best estimator underscore being it's loading for quite a long time. When we printed out best model, looked like it used L1 and C equals 10. That's what it says, the best model. So that should be correct then. We'll see if it's taking quite a long time to load, so we'll see what happens. Oh, fun! So I did define best model. let's, I guess, look once more time in the solution here. Best model. Yep, so exactly what I have. Did I save it and run? Let's do that once more and make sure. I might have just forgotten to save it, which is probably what's true. Yeah, I must have just forgot to save it. Guys, I'm absolutely radiating today. That's what happens when we use Jupyter Notebook, though, because it's all white. And then I have white on this monitor, white on this monitor. I have two monitors, by the way. I don't know if one's for recording, one's for actually doing the stuff. So, okay. Set the score corresponding to the best estimator to the best score. So we can do that by setting it to equal to CLF dot best underscore score underscore. And then we're going to set the value of test score, the accuracy. It wants the accuracy. Store that in test score. Calculate the accuracy of the best estimator on the test data. How do we do the test score? What do we set the test score equal to? Calculate the accuracy of the best estimator. How are these scores? I want to look just really quick because if it's something that I should know, I want to know. CLF.score. Oh, didn't know that was a thing. Save, run. How do these scores of the best model compare to the training and test data? So it performed better on the testing data or on the training data than it did on the testing data by about 1.5%. We've successfully performed a grid search over a 2x3 grid of hyperparameters using the CV results. We can look at the scores for each of these. Is a dictionary of values. Use the key argument params to get the list of parameters. Convert this into a pandas data frame named hyperparameter.grid. Use the key argument named to get the list of mean scores corresponding. What does it want me to do to create the hyperparameter grid? So it wants me to create a pandas data frame. So data frame is equal to pd dot data frame of to get a list of the parameters, convert this into a data frame named hyperparameter underscore grid pandas data frame using clf.cv underscore results underscore and only taking the params column. Look at the scores for each value of the hyper. Use the key argument mean test score to get the list of mean test scores corresponding to the parameter values. Convert this into a single column peg. Okay. What does it want me to do? 2 data frames, columns equals score. Okay, so it's very... Okay. I see. So actually, so here's our C value, here's our penalty value, and then here's our score. So again, it would find that 10 and L1 was the best, and that's kind of what we found, right? 10 and L1 was the best. Please hurry up. Please. An introduction to the random search method. We're now going to look at an alternative method to tone hyperparameters, the random search method. With grid search, we made a list of hyperparameter values and tested each of them. What if instead of pre-selected list, we selected some random values? The random search does that and might look like the top half of the image on the right as opposed to an orderly grid, right? So we just kind of check, guess and check. Random search implements random search with cross-validation. 3 arguments. First, the estimator, then the parameter distribution, a dictionary, what specifies the hyperparameters as keys. We instead had parameter grid, a dictionary representing the grid of hyperparameters to search from, specifies the hyperparameters as keys with corresponding distributions to draw lists of values from. And then finally, n iteration, so the number of times the algorithm needs to randomly draw these distributions. The default is 10. Using randomized search.cv, when we want to use grid search, we made a list of different hyperparameter values. With random search, we don't have to make a list. We still have to provide some information about how we want to select the random stuff. Do we want random numbers between 0 and 100, between negative 10 and 10? Do we want the same chance of picking small numbers and picking large numbers? We can do this by specifying probability distribution for each hyperparameter. So let's take a closer look at each distribution. The penalty hyperparameter of scikit-learn's logistic regression model only has 2 possible values, L1 and L2. We want to list them. We list them both. Randomized search will treat this as a discrete uniform distribution. That means every item has an equal chance of being selected. The hyperparameter C is the inverse of the regularization. It can be any positive number, so we want to specify a probability distribution that allows us to randomly select a positive number. The SciPy library has many probability distributions to choose from. You can see a list of them. For example, we're using the uniform distribution, allows us to randomly select number between LOC and LOC plus scale. And in this case, 0 and 100. Run the code under setup cell to import libraries. Okay, so we'll run this. And we'll first create our dictionary called distributions. Distributions will have the keyword penalty and C. And for the penalty one, it's going to be the L1 and L2. For C, though, we're going to do it a little bit differently. We want it to be uniform distribution between LOC equals 0 and scale equals 100. Guess I don't need the spaces in here. We can now save this, run it, test our work. Okay, let's do a couple of draws from the distribution C to make sure we do get numbers between 0 and 1. Create an array. First draw to use .rvs to generate 10 random variables for C from the distribution's dictionary. Repeat the same process but with an array named second draw. So first draw is equal to distributions, and we're checking the C.rvs 10 just by 10. This is second draw. Let's see if I did it right. I mean, it was definitely a big shot in the dark here with what I'm doing, but they're not really specifying. It just says random values. I'm assuming that means random value selected. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I did it right, to be honest. I'm feeling pretty happy if I did that right. Oh my god, I'm so good. Let me check the hint and make sure. Oh my god, I'm so good. I'm so good! We're now ready to create a random model, right? So let's first create a logistic regression model like we've done in the previous exercises. And it looks like we're going to have a couple parameters. First, we're going to put solver is equal to lib linear, and that's because we want to both specify that it could be an L1 or an L2 regularization. So only if we didn't specify that it was lib linear, then it would not be able to use the L1. Would only be able to use L2. We're setting max iteration equal to 1000. It wants me to now create a search model called CLF, randomized search CV, using the parameters LR, distributions, and n iter is equal to 8. We'll save that. We'll run it. Oh. Cool. Evaluating the results of randomized search CV, we can now follow a similar process to what we did with grid search CV to evaluate the results of randomized search CV. After fitting a randomized search CV model, we can find out the results of using the following attributes of the CLF argument. Best estimator gives us the best estimator, best score, best parameters. We've seen all this, and additionally .CV results attributes gives us the score. After running the setup cell, which we can do really quick, we'll run it. Fit the model, so we'll do that by doing clf.fit to the x train and y train variables. Then we'll say best model is equal to clf dot best underscore estimator underscore. We'll then uncomment the print lines here. We'll click run and save. In this case, it looks like when we had a C value of 79 and a penalty of L1, we did pretty well. It's loading really quick. Can continue on here, best score underscore, and then in this one with the test, score would have been equal to clf.score with the x test and y test data. Save, run. It looks like, again, they're very similar. Very, very similar, which is good. And we're going to do another pandas data frame, hyperparameter values is equal to pd.data frame with the values of clf.cv underscore results params, and it probably will want me to create another one, random search scores is equal to pd dot data frame clf.cv underscore results underscore actually, but this time with the value of mean test score, and we want columns to be equal to score, so columns equal to score. We'll save this and we actually want to print this stuff out, so we'll save it now and then run it, and it'll print out the data frame, and we'll be able to find that that value is the same. We can now click test work. We should be absolutely gaming. It does not help right now that I am absolutely getting obliterated by this light. I don't know why it's like that. I think if I had like a piece of paper right here, it would be fine, but for some reason it's blowing it up. Don't know enough. Nice work. Machine learning hyperparameters, example of hyperparameters, grid search, random search. Both of these are known as k-fold cross-validation. Let's take a peek at what's up next. Let's do this quiz. Fill in the code to create a randomized search model called RANSearch that uses the model CLF and dictionary distributions. Okay, so we can say RANSearch is equal to this, and then we would first specify CLF as our argument because that is the model that we're using. And then we'd use distributions. Below is some pseudocode involving grid search and grid output. Based on the code and output, what are the following statements is false? Choosing random values for parameter 1 and parameter 2. I wouldn't say it's random values because it's grid, so it's going to test all of them, right? So random values wouldn't be right. Which of the following options best describes the grid search algorithm? Grid search tests a machine learning algorithm on randomly chose hyperparameters. No. Grid search tests a machine learning algorithm on specific list of parameters. That's maybe true. Works by guessing how. No, let's be this one. Fill in the code that will print an estimator chosen by the random search algorithm. Print the estimator chosen. Okay, so we have a random search. We fit it here, so it would be CLF dot best score, and then we want to print that out, right? Print it out. That's unfortunate. Fill in the code to create a dictionary called distributions that will be used. So first we'll have penalty and then uniform. We'll say LOC is equal to 1, scale is equal to between 1 and 5. So we would do scale is equal to 4. Import uniform. Nice. Let's take a peek at the one I got wrong here. It's actually best estimator. And I should have known that. It says estimator, not best score. All right, we got a bit of a project here, which always is very fun, very exciting. Let's take a peek here. I think this will be the last part of this chapter. Looks like it's going to take about 20 minutes. So, all right. The data set has some libraries. You've been loaded at the sun, loaded at the setup cell. I don't know where I got sun, but run the setup cell to get started. We've run it, and we see that's what the pandas data frame looks like. Create the predictor and target variables and label them X and Y respectively. So let's first see what it wants us to actually do. There are two types of arrays and types. So it would be, which variable are we trying to go on? That's the question, right? You're going to use the data set techniques in two arrays and grain types. Class. I would assume that the y variable is the class variable. So it would be, what do we call this? Raisins class. And then x would be equal to raisins dot drop class, right? Is that a thing? That's how it works, right? Yeah, no, it's not. Yeah, key error class. Oh, it might be because I'm being stupid here. Let's do, instead of dot drop, we'll do all the other ones. So we'll have area. I'm sure there's a faster way to do this, but I'm not going to look it up right now. Major axis length, minor axis length, eccentricity, convex area, extent, perimeter. Cool. Guess we'll do that instead. And that works. Okay. Data sets. So raisins dot the number of features. Is it just one? I guess we can just do x dot the total number of features length dot of x. Let's see what happens if I do that. Number of samples, the length of x or y gives this total number of raisins in the data set. Okay, so this is samples above that, though, we would print features, and then it would be length of x dot columns, and then finally samples belonging to class 1. So it'd be print samples belonging class 1. So for this one, it would be the sum of the target variable. Oh, I guess that makes sense because the rest are 0. So you could do sum of y, just sum y. And I think that works. Split the training and test into train and test data sets with a RAM set of 99. Okay, so train, test, split, and we'll say that we want x train, y train, x test, y test, and we're saying that we'll do x, y, random state equal to 19. I think that's it. Yeah. All right. A decision tree classifier works well for binary balanced classification problems. Initialize a decision tree called tree. Lovely. I hated decision trees. Tree is equal to decision tree classifier. And I assume we put X and Y. X. Well, do we fit the model first? Oh, I didn't do this one yet. Okay, I didn't even look at 6 yet. So, I assume the decision tree classifier is just, yeah. Okay. Well, so far we'll save, just so we can know that we're correct, right? Dictionary of parameters. So, implementation of scikit-learn has many parameters. Create a dictionary parameters. Parameters is equal to a dictionary. And has max depth. Explore the values of 3, 5, and 7 for this. And then the other one we want min samples split. And we want exploring the values of 2, 3, 4 for this. If we run that, is that good? Oh. Am I spelling it wrong? Yes, I'm adding an S for no reason. Something tells me that I'm going to want to put something else besides just tree. I guess we'll just keep going until something doesn't work. I guess maybe not. Because we're specifying the training here when we do grid.fit. We now want to print the model's stuff, print the best estimator, print the results. Print grid.best estimator. It wants me to also print grid.best underscore score. Print the result, print the best score on the and the score of the test data. Okay, so we can do that by printing grid.score on X test and Y test. And then what it wants, then what it wants me to do is print a table summarizing the results, use to get the score of each parameters, get the score. Okay, so it wants me to create 2 data frames. I'm going to say df1 is equal to pd.data frame using grid.cv underscore results underscore at params, and then df2 is equal to pd.data frame of grid.cv underscore results underscore at the mean test score, and commonly we do columns is equal to score. Then we can do pd.concat, and with the pd.concat, that doesn't help me. I assume we're just going to do the two data frames, df1, df2, and then we can save this to a variable, assume called mod table, and then what, print table. Okay, grid is not defined. I might need to go back here quick. Run. Uh-oh, not good. Uh-oh. Did I not do this right? When we fit the model to X-train and Y-training data. Okay, let's go back, I guess. Split the training data in X-train and Y-train, and the test data X-test and X-Y-train. Is that not what I did? Found input variables with inconsistent number of samples. Checked consistent length, return result. If we get unstuck. Let's rerun everything. Yeah. So it's having an issue with grid.fit when we do the training data, which is interesting. Grid search CV would be create the grid search CV model. Grid is equal to grid search CV. The model, which we've declared as tree, is decision tree classifier. And then we fit it. I'm a little confused on what is going wrong here. Grid is equal to grid search.tv. What happens if we do this? Fit the grid search model to the training data. So grid.fit to the training data X, training data Y. That's what I have, right? But it's having an issue with that. And I'm not sure why. I don't believe it would be the random state. Train test split on X and Y. X and Y. Do that back. Yeah, it's really having an issue here. If length of uniques is greater than 1. I'm trying to read it, but I don't think I'm going to be able to. This is something that's annoying. There's a... I thought there might be an example. There's not really any help for this one, unfortunately, as well. Yeah, that's not going to help us, unfortunately. Yeah, I'm not really exactly sure what to do here. I'm doing exactly what the hint says. I'm creating a grid object that's grid search CV. Doing that. The parameter dictionary is right here. Let's try changing the random state to 20 and let's just see what happens. Maybe something different happens. Yeah, no, it's the same thing. It doesn't really matter. Let's make sure this is correct. Hyperparameter 1, all values. Set up a dictionary of hyperparameters, search for the search. The pseudocode is parameters equal to hyperparameter 1, value 1, value 2, value 3. Value 1, value 2. I don't know why it's doing this. I don't know why it would do that. Dot, dot. All right, dot, dot. Fuck it at this point. Yeah, invalid syntax. That just doesn't make any sense. Found output in variables with inconsistent number of samples. Unfortunately, folks, I'm not so sure what to do. There's no way to kind of get around this right now. I think we were doing everything correct. I don't see any errors right now, unless I'm supposed to specify something within decision tree classifier. But that's going to just have to do it for today's video. I'm going to have to skip the rest of this just because I don't know what else to do. We're very much stuck. I spent like 10 minutes just kind of staring at it there. In the next video, we're going to do ensembling methods. So we'll learn about that. We're very close to the end. We're about 90% of the way through the course. I'm pretty happy about that. If you did enjoy the video, please be sure to give it a like. See you in the next one. Peace out.